So this one we were looking at, right? Yeah. Okay. So this was the following questions we asked last time, and now we'll answer. All right. All right. So we were looking at S2 with the equivalence relation. Let me draw that again. All right. Yeah. So this is the best I can make. Right. So, suppose this is, well, suppose this is x axis, this is y axis, and this is z axis. All right. So now the identification is as follows, as we did. So pick a point here, and this is getting identified here with something here, the other side of it. So this point get identified with this point. This is lying outside other side. So this is the point x, y, z. Then this point will be minus x, minus y, and minus z. All right. So this is called antibodal point to x, y, z. All right. So this is antipodal identification. All right. So now this question was whether this is a house drop, second countable, and local Euclidean. All right. All right. So let us go to this projection map. So we have this. Well, before going further, let us describe few things also. So this x, y, z. Just 1 minute. Sorry. Okay. So this was antipodal identification. So xyz is identified with minus x, minus y, minus z. All right. Now this is an equivalence relation. So you can quotient with this. as we mentioned last time as well. So yeah. So now we look at this S S2 cosented with this one, right? Now look at the picture. So look at the picture again. So look at the picture again. So this is nothing but, see, all this point downstairs, lower hemisphere is identified with the points in the upper hemisphere. All right. So the point is, why don't we just look at just upper hemisphere, right? And the boundary and the circle in the xy plane, right? So this is homeomorphic to to h concentrated with this, where h is collection of all x, y, z in S2 such that z greater or equal to 0, right? And x, y, z well x, y, 0 identified with minus x minus y comma 0. The other points are not, I mean, you do not need to identify other points, right? So here h is nothing but the upper part, right? So this is upper part. So here these points need not be identified. The only points here are identified. So we have this x-axis and we have this y-axis, and these points gets identified with these points. So let me take a different color here. So these points identified with these points identified with this one. So it's something like this. The antipodal points. These are identified. Yeah, is it clear? Any question? So this is the identification, right? What will be this map? So by homeomorphism, you need to define a map, right? So S2 cosented with this, you have to give a map to H cosented with this. So what is this map? Can you give any answer?
Sir, x, y, z goes to mod x, mod y, mod z.
Why is that so?
No. X, y, z goes to just z coordinate mod. So just make that thing positive.
Okay. All right. Right. So XYZ will go to XY. Right. So here you see you cannot write in this fashion. So what you need to write a class. So the equivalence class, this goes to Here one can write mod z, as you said. Yeah, right. So that exercise, so that this map is a homeomorphism. Now, even further, you see this one can be mapped to the disk, right? The upper hemisphere is homeomorphic to the disk, unit disk, right? So H is homeo to disk. Let's say call it. Okay, so this is call this as F, and this is G. Let's say. Now this is how does it go? It go well. Any point here, H looks like x, y, 1 minus x square minus y square, right? That goes to x comma y. So this is a homeomorphism. So this is G. So that G is a homeomorphism and G induces a homeomorphism G bar from H with D concentrated with this, where the equivalence relation this on D is as follows. So what is the equivalence relation on D? I didn't mention what is D. So D is x, y in R2 such that x square plus y square less or equal to 1. Closed unit disk. Yeah, so what will be the equivalence relation on D? So let me write what is D. D is this one, x, y in R2 such that x square plus y square is less or equal to 1. Come on, say somebody.
If they are diametrically opposite.
Oh, so what will be the map? xy identified with
minus x comma minus y.
minus x comma minus y. Right. Of course. So this is D x y, and you are identifying this point to this point, right? This point to this point, and so on. This point to this point, this point to this point, right? Yeah. All right. Why am I doing all this? Right? So this is something, some known object. Well, might not be known till now for you, but once you know it, then it will be known from that time onwards. So see this, instead of looking at the disk, one could look at the lines, right? So here what we like to do is look at R3. Look at R3. The same thing again. Look at R3 minus the origin. All right. Call this as S, right? And X, Y. Let's take in S. X is identified with Y if there exists T in real number minus the origin such that X is Ty. Or rather, I would write Y is equal to Tx. So do you see what is this in R3? What are these equivalence classes under this? So this is an equivalence relation. So exercise, show that this is a simple exercise, the first year program. This is an equivalence relation on R3 minus the origin. Now, what are the equivalence classes? Can you tell me? Anybody?
Straight lines passing through 0.
Right. The real lines passing through the origin. Right? So, is everybody clear that these are actually equivalence classes? Or actually, you are looking at equivalence class means actually every points in that line. So you get the whole line passing through origin, but origin of course not there in the space, but that whole line, all the points except the origin in that line becomes one class. Yeah. Any question here? All right. So you look at this. So I'll not use S. So I'll just use this one and quotient with this one. It has a name. RP2. So this is the name is the real projective space of dimension 2. So now so why I'm doing this? I'm doing because this RP2 is also, one can give a map homeomorphic to the other things, right? S2 cosented with that. So what can you give a map here? Have anybody seen this? Yeah.
Yes, sir. If we normalize the thing to unit, we'll get a map.
Right. So what you get? You need to look at first R3 minus the origin to S2. So first look at this one. X, Y, Z goes to X by X square plus Y square plus z square, y by x square plus y square plus z square, comma z by x square plus y square plus z square. This one. All right. So that, so this is a map. This is on to map. All right. Now this map, let's call it psi. So what you need to show that psi induces. So in this case, psi is not a homeomorphism, induces, but it takes a class here under this equivalence class to equivalence class there, induces a homeomorphism. In the questions. All right, so this is an exercise in topology actually. Okay, so now we generalize this. Now generalize the above construction in Rn plus 1. So you consider this Rn plus 1 minus the origin. This is the space, and xy in Rn plus 1 minus the origin. For this, you give an equivalence relation or give a relation if there exists t in r minus the origin such that y equal to tx. Right? Y equal to tx gives you a line. So that's why each equivalence classes will be a line. All right. Now again, this becomes an equivalence relation. Again, this becomes an equivalence relation. And RPN, the real projective space, RPN is defined by Rn plus 1 minus 0 cocentered with this. All right. Now let's come to the question. What are the open sets? Right? You know the open sets. You need to so open sets. What are open sets? So you have cosine map pi from Rn plus 1 minus the origin to Rpn. U subset Rpn is open if pi inverse U is open in Rn plus 1 minus 0. All right. This is the definition of open sets in the cosine topology. So that's how one gets cosine topology, right? So open sets are this. Now, once we know the open sets, then we need to talk about whether these are house drops, second countable, etc., etc. Right? Now, any idea whether this is house drop? The topology in quotient topology, right? So that's how one gets the quotient topology in RPN. Right? So now any idea about house dropness? Oh, by the way, before going into further, let us look at, so what is RP1? What is RP1? It's nothing but the collection of
A circle.
circle, right? Lines of R2 passing through the origin. All right. Now this is also identified as S1 and the antipodal identification XY and the antipodal identification this goes to this goes to this, which is nothing but you see this is homeo. Look at half circle and these 2 points are identified. These 2 points are identified. These 2 points. These 2 points identified. So hence what you get is actually the unit circle again. This one. All right. These are topological facts. In quotient topology, you might have studied it, right? So did you study these things in quotient topology? Did you study in the quotient topology? You guys don't remember. Anyway, that's fine. So all right. So now house dropness. Can you give house dropness? So whether RPN is house drop. Is it house drop? Any guess?
Yes, sir. Sir, I think like the guess would be like if I have 2 points, then you can have cones from the origin
Mm-hmm.
as you open sets that will not intersect.
Right. Yeah. So the point is, yeah, something like this. So if you have a line passing through the origin, look at an open region. Look at, so this gives you a point in the quotient topology. And suppose This is another one which gives you one other point in cosine topology. And so what you need to consider is an open cone around this white line. Open cone. And an open cone around this line. All right, so these are open cones that do not intersect. Now open cones are open sets in Rn minus 0, right? So these are open sets. Now the problem is, there's a problem, right? And you want to look at the image under pi, right, to Rpn. So xy lying in Rpn gives you two lines. So x corresponds to here, this line, and y corresponds to this line. All right, now these two lines corresponds to the well, then you have two open sets in Rpn, sorry, not in Rpn, in Rn minus 1, Rn plus 1 minus 0. So you have two open cones in Rn plus 1 minus 0 which are disjoint, because this is very simple to calculate, to do, right? Now the question is, the claim is that, let's call this one u and this one v, right? V. Now claim is, so claim pi u intersection pi v is empty, right? Well, it is empty. That is simple, right? It is empty. Now what is the problem? This is empty, right? This is not just, this is empty by construction. Well, so this is not a claim. So this is by construction. This is by construction. This is empty. So what is the problem? So the problem is whether pi u and pi v are open sets, right? So enough to show pi u and pi v are open sets. All right. Now is it open set? Are these open set?
Yes,
Any
sir.
idea? Why?
Sir, when we take pi u, then this will be open if pi inverse of pi u is open.
Right.
And we can see that pi inverse of pi u is u itself.
No, it's not true that pi inverse. Acha, pi inverse of pi u is just u. That's what you mean, right?
Yes, sir.
How do you see it?
Sir, like take any point and like because we're taking the cone. The construction of the cone is exactly in that way.
Right, right. That is true. So, but we'll prove a more general one. So, a proposition, the projection pi from Rn plus 1 minus the origin to Rpn is an open map. Right? This is an open map. So that is a proof. Let U be open in Rn plus 1 minus origin, right? To show pi U is open in Rpn. So which means that is so we need to show pi inverse of pi U is open in Rn plus 1 minus the origin, right? Now what is pi inverse of pi U? Is it used itself?
No, U union TU, I think.
Yeah, Praful, you say that again.
Sir, U union
U union. Yeah. Yeah, Abhishek was saying something. Yeah, say that again. Just again, I'm sorry, just 1 minute.
TU. Because
Yeah, say that again. Praful, I can't hear you. Hello? Can you guys hear me?
Yes, sir.
Yes, sir, we can hear you. His net has some problem, I think.
Yeah. Yeah, he joined again. So, Praful, can you say what you are saying?
hello.
Yeah.
Sir, I was saying U union TU for any T.
For any T, what? What is T?
The way we have defined map pi.
No, what is T?
T for any T in R minus 0.
Okay. Yeah, that's correct. That's correct. So this is nothing but union T belongs to R minus the origin and means TU. T equal to 1. At T equal to 1, you get U.
Yeah, correct.
So this is which is open in. So you get actually cone, right? You have it. You have U, and you look at the cone. Whatever cone you can have containing U, and and also the containing U and the minus U. U is identified with minus U all the time, definitely. So the opposite. So you take the cone around U and take the cone the on other side as well, and that's what you get here. So which is open in Rn plus 1 minus the origin. All right, so this is open. Hence, this implies pi is an open map. So once pi is an open map, you get this Hausdorffness. So therefore, we get that RPL is Hausdorff. All right. Now, what about second countability? So here I'll quote a theorem whose proof you might have seen. If you have not seen, you just see as an exercise. So this is a theorem from quotient topology. Suppose this is an equivalence relation on a topological space S, and pi from S to S quotient is an open map if B is B alpha. This is a basis for S, then the set pi of B alpha is a basis for S quotient with this. So proof is an exercise. All right, so let's take a break for 10 minutes and then we'll meet again. So 11 minutes actually. We'll meet at 6:20 and we'll show that these are this is local Euclidean, and we'll give an atlas there. Okay. Okay then.